Welcome to the Cal Corporation's series of videos about software engineering. The topic of this video is C++'s Lambda syntax. Before proceeding, make sure that you have already watched these other videos first. This traditional initialization statement has three parts: a type name, int, the name of the variable being defined, and a literal value. For a callable object variable, it also has a data type, as we've discussed in a previous video. The literal form of a callable object is called a lambda. A lambda's syntax is square brackets, followed by parentheses, followed by braces. Like any function, you can specify a list of parameters inside those parentheses, and you write the function's body of statements inside those braces. Notice that you do not specify the lambda's return type, however. Instead, it is always automatically deduced using the type deduction rules of C++11's auto. If a lambda isn't going to have any parameters, then you could either write empty parentheses, or you could omit those parentheses symbols. A lambda's body can use any static variable without doing anything special. But if a lambda's body wants to use any non-static variables from its enclosing scope, then the lambda must first capture those variables. There are two possible methods of capturing: either capturing by reference or capturing by copied value. Inside the square brackets, the programmer chooses which capturing method he wants to use for that variable. Because this example lambda's body uses the local variable I incremented, this lambda needs to capture that variable. Because we're preceding its capture declaration by an ampersand symbol, the I incremented variable will be captured by reference. What happens is that, as the callable object variable is being initialized, this lambda is evaluated. When this lambda is evaluated, C++ will establish a reference to the I incremented variable's definition. That I incremented variable had been defined in the enclosing scope. Later on, our software calls the callable object. Of course, when that call happens, the body of statements are done. Anywhere that the statement body was programmed to use the I incremented identifier, the procedure will make usage of that reference to I incremented in the enclosing scope. That reference was not a constant reference. The statement body is able to use that reference for modifying the I incremented variable, and that change will be observed in the enclosing scope. In fact, any other changes that might happen to the I incremented variable in the enclosing scope will also be seen by this lambda's body when we call the callable object a second time. Now, let's introduce another variable. But this time, we won't type the ampersand symbol. So this iStep variable will be captured by copied value. Remember that this lambda is evaluated while the callable object variable is being initialized. When this lambda is evaluated, that local iStep variable is also evaluated. At that point in time, iStep evaluates to 2. This lambda copies that value of 2 and remembers it in its own memory storage. Later on, our software calls the callable object. Anywhere that the statement body was programmed to use the iStep identifier, the procedure does not interact with the actual iStep variable. Instead, where the statement body has the iStep identifier, this lambda uses its remembered value of 2. This lambda's remembered storage of the copied value of 2 is something kind of like a compiler temporary, at least in the sense that the compiler owns it. You, the programmer, are not allowed to modify something that has been captured by copied value. Of course, your enclosing scope can modify the actual iStep variable, where that value of 2 had been copied from, but modifying the actual iStep variable does not change the fact that this lambda is still remembering a value of 2. When we call the callable object a second time, this procedure will still be increasing things using a step size of only 2. When capturing by copied value, if you do want this lambda's statement block to be able to modify this lambda's remembered storage, then you can request that ability by typing the mutable keyword. Then, if your statement block's programming makes any modifications to iStep, those modifications are retained. They will still exist the next time the statement block is done, which might modify iStep again. This feature gives the Lambda some kind of personal modifiable memory capability. Be aware that even when you're using the mutable keyword to gain that privilege to modify, there is still no connection between the Lambda's remembered storage versus the actual iStep variable where the value originally was copied from. Even after this Lambda has been modifying its own remembered storage, the actual iStep variable still has its original unmodified value in the enclosing scope. In case you have a lot of variables that all need to be captured from the enclosing scope, there's a shortcut syntax that you could use. You can specify the ampersand symbol by itself without being adjacent to any variable name. Doing that causes all of the enclosing scope's variables to all be captured. They will be captured by reference. There is a similar shortcut that uses the equal symbol instead of the ampersand symbol. Again, all of the enclosing scope's variables will be captured, but this time they will all be captured by copied value. There's also a way to specify capturing ivar0 and ivar1 by copied value, but capturing everything else by reference. Or capturing ivar0 and ivar1 by reference, but capturing everything else by copied value. The same capture by copied value notation could also be used for another purpose. It could be used to capture a compiler temporary value which results from any general C++ expression. When the lambda in this example is being evaluated, the I step divided by 2 expression is also evaluated at that time. The result of that evaluation is a value of 2. Again, this lambda maintains some remembered storage in which it remembers that value of 2. The data type of that remembered storage is never specified by the programmer. Instead, it's automatically deduced using the same mechanism as C++11's auto.